the Zoom session. And for everyone who missed it, I have the GitHub link in the chat. Please download all three files. Or if you have GitHub cloned, then you can just do git pull. I'll show you guys the video for today. Can everyone see this? And let me know if you guys hear it.
Yesterday, a man in a black suit
You guys hear it? Yeah, okay. Then we'll get started.
Yesterday, a man in a black suit left this strange looking device on my doorstep. It appears to be some kind of futuristic brain scanner. Now, I've been writing code for nearly 2 decades, but one thing I've never done is use my brain. That might be why all of my side projects fail, but today that changes, because today we're going to do something that has never been done before. Instead of coding with my 10 old arthritis-riddled fingers, I'm going to give Claude Code full access to my brainwaves, with no filters and no safeguards, just raw, uncut gamma energy running at 256 Hz is straight from the squishy encephalon inside my skull. The coding agent will then use this data to vibe code a JavaScript app for me on the fly. It's part science experiment, part tech horror movie, and 100% guaranteed to make your privacy lawyer cry. It is November 12th, 2025, and you're watching the Code Report. I've been on the wait list to get one of Elon's Neuralink brain chips installed, but the reality is that I'll probably get a Tesla Roadster before that happens. Luckily though, if you want to capture and analyze your brainwaves, there's a far better alternative that doesn't require invasive robot surgery. It's called the Neurosity Crown, a stylish electroencephalography device that can measure the electrical activity happening in your brain. I made a video about this thing a couple years ago back in the old GPT-4 era, but this time Neurosity was kind enough to sponsor the video and provide me with their latest limited edition device. To understand how this device works though, we first need to learn a little bit about brain science. When you're asleep, your brain is vibing at low frequency delta waves around 2 Hz. As you wake up and chill out, those waves speed up to alpha mode, roughly 10 Hz. But when you lock in, like solving math problems or cranking out code, your brain shifts into overdrive, gamma waves hitting up to 35 Hz. These gamma waves are where the real magic happens. The wave patterns constantly shift with your focus, mood, stress, and environment, producing a live data stream of your mind's chaos. And that's where the crown comes in. It can literally analyze your brain and detect distinct thought patterns, like that feeling when you bite into a sour lemon, left-hand pinch, jumping jacks, mental math, and so on. It does this by training its algorithm on your mental signals. All you have to do is think it, relax, repeat about 30 times, and then it's trained to detect your specific thoughts. But now here's the crazy part. They just released an MCP server that can easily connect your brain activity to any AI agent. That means you can let a tool like Claude Code tap into your brain activity and analyze it, or use it as context in any prompt. All you have to do is set up the Crown device, then open up Claude Code and add the Neurosity connector. And now your neurologist with 20 years of medical training is completely obsolete, because we can just go right into Claude and now analyze our brainwaves. Apparently, it determined that my delta and alpha waves were high, which I thought was a good thing, but actually it means I must be half asleep, or maybe this whole video is just a dream and nothing is actually real. In either case, now let's have Claude update my portfolio website based on my brain's actual profile. As you can see here, it generated this beautiful dreamlike website that perfectly represents my current vibe. That's cool and all, but the real power comes from the Neurosity SDK, which allows us to tap into our brains programmatically. That means in theory, I could do something like this, where I use Kinesis to subscribe to a thought, like left-hand pinch. Whenever that thought occurs, it will run this callback function, and that code could do anything, like turn off a light in your smart home, invest in stocks with a trading API, or even write code for you. Like in this demo, I have a function that will make a call out to the Claude API whenever I think about my left foot. What that will do is send Claude whatever code I've highlighted and tell it to automatically refactor that code. In addition, I can also subscribe to the thought of a sour lemon and have it automatically discard that code if the code sucks. In other words, we're literally vibe coding here. The coding agent's actions are based on our thoughts and our vibes, not our actual commands. I wouldn't say this is the optimal way to write code, but who knows where this technology is going to go in the future. Huge thanks to Neurosity for making this video possible, and get your own Crown device using the link below. This has been the Code Report. Thanks for watching, and I will see you in the next one.
Anyone have any questions about it? If not, we'll just get started. Okay, so does everyone remember where we left off at? Can you guys see my screen? Okay, so last time we left off at tic-tac-toe. We did everything from initializing the board, make move. Here we check the winner, we check if it's draw, we get all the available moves, we do pretty print, and we have AI move, which we didn't fully implement. All we did was do random.choice, which basically is just probability, flip a coin and then choose a random move. And we have play game. Today we'll finish off this AI move and create an actual AI. Any questions here? Or need any recall any functions that I have to explain to you guys? If not, we'll get started with Minimax. Okay, if no one has any questions, I was gonna start off with a quick video, a video on Minimax and alpha beta search. I mean, alpha beta pruning. That will explain to you guys at least vaguely about how to implement this. And we'll go ahead after this video and actually implement the functions. Does that make sense? And this video is in the class page. Okay,
Say we want to write a program that can play some turn-based game like...
can you guys hear it? Are you guys able to hear it? Okay.
chess. One aspect of this is the search algorithm, which is what allows the program to look ahead at possible future positions before deciding what move it wants to make in the current position. This white dot represents some position in our game with the white side to move. To keep things simple, let's say that in every position there are only two possible moves to choose between. We can visualize these moves as two separate branches, at the end of which are two new positions, where it's now, of course, black's turn to move. We can continue expanding the tree of moves until either we reach the end of the game, or we decide to stop because going deeper would take too much time. Either way, at the end of the tree we now need to perform a static evaluation on these final positions. A static evaluation just means trying to estimate how good the position is for one side without making any more moves. For example, a crude approach in chess would be to add up the values of the remaining white pieces and subtract from that the values of all the remaining black pieces. So large values would favor white, while small values would favor black. For this reason, white is always trying to maximize the evaluation, while black is trying to minimize it. So let's start with these two positions on the bottom left. Say we evaluate them and they come out as -1 and +3. Well, in the previous position it was white's turn to move, and since white will of course choose the move that leads to the highest evaluation, we can assign this position a value of 3 as well. Next, let's evaluate these two positions, and say we get +5 and +1. Once again, from the previous position white would pick the move leading to the highest evaluation, and so we can assign it a value of 5. We've now evaluated both the positions stemming from this position, where it's black's turn to move. Black will choose the move that leads to the lowest evaluation, and so we can assign this position a value of 3. I'll very quickly step through the other half of the tree. Say we evaluate these as -6 and -4, white will pick the -4. The next two positions are evaluated as 0 and 9, so white will pick the 9, and between -4 and 9, black will pick -4. At last we've arrived at the top of the tree, where we can see that white should choose the move on the left, since that way, even if black plays the best move, white will still get a +3 position. So now that the basic idea is hopefully clear, let's look at how this is implemented in code. We have a function called Minimax, which takes in the current position, a depth for how many moves ahead we want to search, and a bool called maximizing player. We begin by checking if depth is equal to 0, or if the game is over in the current position, in which case we return the static evaluation of that position. Otherwise, if it's currently the turn of the maximizing player, which in our example means it's white to move, then we want to find the highest evaluation that can be obtained from this position. So we create a variable called maxEvaluation and initialize that to -infinity. We then loop through all the children of the current position, and by children I just mean the positions that can be reached in a single move. To find the evaluation of each child, we make a recursive call to the Minimax function, passing in the child, depth -1, and false, since it will now be the other player's turn to move. We can then set max eval equal to whichever is greater between the current max evaluation and the evaluation of the child position. Once we've evaluated all the children, we can return the maximum evaluation that we found. Now, we do essentially the same thing for the minimizing player, creating min eval set initially to positive infinity, and for each child position we call minimax, passing in the child, depth -1, and this time true. Min eval then gets set to whichever is smaller between the current minimum evaluation and the child evaluation, and finally we return the min evaluation. Let's step through this example again, this time with the code in front of us. First though, we'll need an initial call to the Minimax algorithm to start things off. Okay, we're at the first position and we want to find the max of the two children, so we call Minimax on the first child. It wants to find the min of its two children, so it calls Minimax on its first child, which in turn wants to find the max of its two children, so it calls Minimax on the first. At this point though, depth is equal to 0, so Minimax returns the static evaluation of that position. This value gets passed up to the parent, which then calls Minimax on its second child, receives the static evaluation from that, and returns the max between the two children. That value gets passed up to its parent, which now calls Minimax on its second child. Minimax is called on its two children, getting their static evaluations, and the max is passed up to the parent, which passes the min of its two children up to its parent, which now calls Minimax on its second child. I'll stop with the blow-by-blow narration now, but hopefully it's quite clear how the algorithm uses recursion to search through the tree. Now that we've seen how plain Minimax works, let's run through this example yet again to look at how it can be sped up using pruning. These first few steps are the same as before, but consider the situation we have after evaluating this +5 position. Without yet evaluating the other position, we know that white can at least get a 5 from here, so we can mark this position as being greater than or equal to 5. We can now see that black won't go down this branch because he already has a better option available. This observation means that we don't have to waste any computation on evaluating this final position, we can simply pretend it doesn't exist. In other words, we've pruned it from the tree. Things now continue as normal again for a few steps until we get here. Black to play in this position will be choosing whichever of the two moves leads to the lowest evaluation, so we know the evaluation here is going to be less than or equal to -4. We can now be sure that white won't go down this branch because he already has a better option available to him, and so we can prune these positions. As you can see, the result of the search is exactly the same as before, we've just saved some time by not considering positions when they can't affect the outcome. Okay, I want to quickly go through a slightly deeper tree. I'll just fly through these first few steps because there's no pruning happening, so it's quite straightforward. In fact, it is actually kind of interesting that we've gone through half the tree and haven't been able to prune a single position yet. So pruning isn't guaranteed to occur, it very much depends on what order the moves are in. Ideally, the moves would be ordered from best to worst for the player whose turn it is in that position. For example, if these two moves had been the other way around, we would have been able to prune the second one. For this reason, it's usually a good idea to order the moves based on how likely they are to be good. For example, in chess, capturing a piece with a pawn is very likely to be a good move, and so it would be wise to explore it first. Anyway, let's continue with this tree. So this next position has been evaluated as +1, and now I have a question. Do we need to evaluate the other position here, or can we prune it? If you're in the mood, I'd recommend pausing the video to figure this one out. So without evaluating the other position, we can say for sure that the previous position is less than or equal to 1, since black is of course just going to choose whichever is lowest. This means that white will never go down this particular branch, because if the best he can hope for is a +1, he'd rather just go the other way at the start, where he's guaranteed a +3, so we can indeed prune that position. Alright, let's finish off this tree. Here we got a 5 and a 2, so black would of course choose the 2. That means this position is less than or equal to 2, and so like before, white will never go down this branch since he can get a 3 by going the other way. This means that we can prune the rest of these positions. The tree is now complete, and we can see that with best play from both sides, the game will follow this path. Let's look at how this pruning stuff works in code. We'll start with our original Minimax algorithm and add two parameters called alpha and beta, which will essentially be keeping track of the best score either side can achieve, assuming best play from the opponent. We'll need to update our recursive calls to Minimax to pass in these two new values. Now, for the maximizing player, we'll set alpha to whichever is greater between alpha and the latest evaluation. Then, if beta is less than or equal to alpha, we'll break out of the loop. Similarly, for the minimizing player, we'll set beta equal to whichever is smaller between beta and the latest evaluation, and then once again, if beta is less than or equal to alpha, we'll break out of the loop. To better understand what's going on, let's step through the example one last time. In our initial call to Minimax, we'll pass in -infinity, which is the worst possible score for white, as our value for alpha, and +infinity, the worst possible score for black, as the value for beta. These values get passed down until we reach our first end position. Here, -1 is greater than alpha, so the alpha value of the parent gets set to -1. 3 is then greater than -1, so the alpha value gets updated once again. However, beta is not less than alpha here, so no pruning occurs. Next, in the parent position, beta gets set to 3, and this is passed down to its second child. After evaluating this +5 position, alpha gets set to +5, and now beta is less than alpha. Since in this position it's white to move, beta being less than alpha means that black had a better option available earlier on in the tree, and so we prune. Going back up the tree, alpha gets set to 3 in the first position, so we know white is guaranteed at least a 3, but we need to explore the other side of the tree to see if we can do better than that. So coming down here, neither -6 nor -4 are better options for white, so alpha doesn't change. In the parent position, beta now gets set to -4, which is less than alpha. Since this position is black to move, beta being less than alpha means that white had a better option available earlier on in the tree, and so once again we can prune. We've now completed the tree. So hopefully this video has made sense of the Minimax algorithm and how it can be sped up using this idea of pruning any branches that can't affect the outcome due to the fact that one side will prevent that branch from ever being reached, as they have a better option available earlier in the tree. I'll leave you with the...
Okay, so that was the video. And now we will head into the code and actually implement the Minimax as well as the alpha beta pruning into our tic-tac-toe. So, and we'll also add in an Expectimax. The only difference for Expectimax is instead of kind of pruning, we're gonna just kind of average the values out so that we don't need to actually search the end values and just estimate it. So does everyone have the code downloaded and or like copy and pasted? If not, tell me now. If not, then we'll go ahead. Okay, so today let's start off with Albert. Can you share your screen? And we'll go ahead with minimax.py. And I enabled who can share, yeah, to all participants. Okay, then Adam, can you share your screen?
Still copying.
Okay, then Kaden, if you have it with you. Kaden, you have to open the minimax underscore base dot py. Is it that you're zoomed? Oh, yeah. Okay. Yeah. Also, do you have Copilot open or like, is it on? Try, can you do if? Okay, yeah, you don't have it on. Okay, so I'll just explain the code for you guys first. So we're gonna implement the Minimax. Actually, maybe showing my screen would be better. I'll just share mine first and then you can share yours after. Can you guys see my screen? Okay. Okay, let me zoom in for you guys. Okay. Okay, so basically we're gonna implement the Minimax, which will just be the Minimax function, as well as the AI move function. And all we need to do later is once we finish it, we'll go back to the CLI that we finished last week. We'll just replace this AI move with that Minimax that we complete. And it will work fine. Okay, first, I'll explain the AI move first. So basically we want to choose the best move for the AI. and we'll be using the Minimax algorithm. And it basically returns the coordinates of the best move that it can possibly do. So first, we want to initialize the variables to keep track of the best score and the best move. And then we go through all the squares that are free, which we'll use the get moves board that we implemented well, 2 weeks ago, which is here, get available moves. Basically returns a list of every empty square on the board. And for each free square, we want to simulate the AI using the Minimax. So yeah, it says we call this function, we pass in board, 0, false, AI player, and human player. And this basically returns the score. And after doing each simulation, we get the best score possible and return that best move. Any questions here? If not, I'll show you the Minimax. So the Minimax takes in the board, the def is maximizing AI player and human player. So is maximizing basically means who is the player that is trying to maximize and who is the player that's trying to minimize. And it says here that true means that it's AI's turn to maximize, and false means it's the human's turn to maximize. And AI player and human player is basically what we choose. And so it's O or X. And def is basically how many moves ahead we are. And board is basically the current state of the board. And basically, we want to recursively evaluate the board and return a numeric score. And the higher score is better for the AI. And basically, first, we want to detect if the game is over or if there's a draw and return the score. If the game isn't finished, then we want to generate all the legal moves. So we want to keep simulating one move after one move until the game is finished. And for each move, we want to apply the move to the board. So we make one move. We want to recurse with the opposite player. So this is another random move from the opposite player. And then we want to undo the move and backtrack. And then we want to finally return the maximum score when is maximizing is true. And otherwise, we want to return the minimum score when is maximizing is false. Does that make sense for everyone? I'm going to assume so. And Kaden, you can share your screen again. And we will go ahead with implementing AI move function for the Minimax. And we'll keep on, since we have 6 people here, yeah, we'll get everyone to implement one function each. Okay, go down to AI move. Okay, so first, okay, you're gonna be implementing this function. So first, we want to initialize the variables to keep track of the best score and the best move. So yeah, we want to initialize the best score. We want the best move. And as it says in the to-do, we want the best score to be negative infinity. And the other one, the best move, to be a dummy value. Okay. So you'll need to use the math function, the math library in Python. Have you ever used that before? Yeah. Import math. And then we want to do, okay, let's see if you, or yeah, try to, do you remember which it is? No? Okay. So it's minus math.inf. So it's math. So that's the library. And we use the inf. Yep. Good job. And now we want to make a dummy value for the move, which is actually, it shouldn't be 0. Okay. Go to the tic-tac-toe.py. Uh, click, yeah, yeah. Yep. And then let's go to all the way to the top. You'll see a macro there that says move. Yep, right there, line 14. So here it says that the move is a type here. So this is how you do type analysis. And it basically says that the move is a tuple of two values, one being int and another being int, which are the row and column. So move is a tuple of row and column. So if you go back to the Minimax, oh yeah, so yeah, basically that, but tuple is not a square bracket. Do you know what bracket it is? Yep, it's a circle bracket. You can go back. So let's make a dummy value for this one. Yeah, good job. So yeah, we set the best score, we set the best move. Now we want to go try each loop over each legal move. So let's try and get the legal moves first. So let's set a variable to get all the illegal moves. How do you want to name this? Yep. Although you might want to do legal underscore moves. Yep. And that is another function from our tic-tac-toe.py. Yep. And we basically input a board. Also, since we're working on Minimax right now, we can just copy paste that into the tic-tac-toe py. So do Control A, Control C, go back to tic-tac-toe, go to AI move, highlight the AI move and delete it. Oh, okay, sure. Enter. Uh, Also, one more thing. If you go up, I think you missed the function header for the AI move. I'm not sure. Yeah, you have to delete that 240, line 240. And you have to do that as well. Import math, go to 241, line 241, and delete that AI move. Nope, control backspace. Okay. And then go down. We'll continue on. AI move, which is up right there. 324. And where were we? We want to visit each available move. So we want to loop over each legal move for I in range. One thing here, would you want to call get moves twice? Get available moves twice? Yeah. So legal move. And would this work? Would range of legal move work? One thing is that it wouldn't work because is legal move what kind of data type is legal move? You can also try and hover on a yeah, yeah. It is a list. And if you hover on range, I'm not sure if it shows. Yeah, it doesn't show too well, but basically you can't re oh yeah, hover on it. You see how it says range and then inside the argument it says stop? Basically, you can only input an integer, but we're trying to input into the argument a list, which won't work. So we'll need to, yeah, that could work, but it's a tuple. So you're basically now inputting a tuple. One thing you have to do is get each loop through all of the list, right? You have to loop through each element. So how do we get all the elements? Like, what's uh, do you know another function that can get the length of legal moves? Because we want to, yeah, basically we'll use len. So we'll do range of len of legal move. So this basically is len of legal move is how many kind of moves there are in that list. And basically we pass in this amount to range and the range function basically iterates it from 0 all the way until that length. Do you understand? Or kinda? Okay. Basically, all you have to know is you want to pass in an integer into range, and that integer is how many times you want to loop. But a better way here is try and do for r comma c in legal move. So you don't even need the range nor the len. This will be way better because what we essentially need here is just the row and column of each move. So basically, we don't even need to iterate it. We can just get the values right away. Does that make sense? Okay. So now we want to loop over each row and column. We want to place AI player on the board and call Minimax. So let's go one by one. So let's place the AI player in the board. So how do we place the AI player on the board? Uh, we wouldn't use another function. Do you know of a way to set a value inside of the board? That would add a value. So how do we access the cell in that board? The cell row column that we got from the legal move. Yes. Do you know of a way to get that cell? So we have that board, right? So if you see the AI move, we see that one of its first arguments is board. So we'll do board, and this is basically the board. Now we want to get the board's row column so that we can get that one cell. Do you know how to get that? Uh, that wouldn't work because it's not a function, right? For R and board wouldn't. That would get each row, but we already have the row and column, right? We have the legal moves, which we got from get available moves. Now we got for R. comma C in a legal move. So this is basically the row and column of that one cell. Now we have the board, and now we want to access the board's row and the board's rows column. So do you know of a way that we can get that cell? Okay. Okay. So do you know what data type the board is? Yeah, it's a list of lists. So it's a 2D list. Do you know what a 2D list is? Okay. So of that 2D list, we want to get the row, R row, rf row, where R may be 1, 2, or 0. So let's, how would you access the first row of that board? Do you know? Yeah. Now, how would you access the second? Now, how would you access the rf? Yeah. So that's the board's rf row. Now, how would you access the that row's column, C column? You have the right idea, but you have it in the wrong place. Yes, that's exactly how you would do it. So now we want to set that cell to AI player. How would you do that? Oh, to help you, the AI move input has the AI player. If you see in the arguments, it's right at the top. When you hover down, go down, it still shows the function header. So it's the AI player. Do you see it? It says line 301. Yeah, that one. Yeah, that's good. We can delete that board on 325. And now we can go on to the next step, which is call Minimax. And we want to set that score to the variable that we set, which is best score or score. Let's create a current score. So set current score. It should be in that for loop. And we want to call the minimax. You can hover on it to see what the arguments are. So we need the board, we need the def, we need the def. Def you can set to 0. And then we want, yep, is maximizing, set it to false. And then we have the AI player, we have the human player. You don't need the equal sign. Yep, that's good. Can you hover on it to see what the error is? No. Oh, okay. You see how you're doing def equals is maximizing equals? Usually those need to go at the back, but let's just delete it and just do false. So false, only false. Yep. And that's because inside the function's argument, you cannot set the values as before unset values. So you can only set it after the unset values. Uh, it's the same for the def equals. And next, what do we want to do? We want to revert it. So let's just, for that cell that we set to AI player, we want to revert it back. What value was it before we set it to AI player? Uh, Not really. So if you go to initialize board, what do we append? What is each value? None, right? So the default value of an empty cell is none. So we'll have to revert it back to none. Make sense? Okay. Now we want to update the best score and the best move. So let's check if it's a better move. So we have the scores, right? We have the current score, we have the best score. So check if it is better. Yep. If current score is greater than best score, then what do we want to do? We want to set it. We want to set best move. Also, one thing you always kind of seem to do, you always have that equals equals sign. That's only for conditionals. Yep. I think that's a habit. But let's also set the best move. Oh, no, that's all good. You're actually setting the best move to current score. You should set the best score to, yeah, and then now we want to set the best move. What would the best move be? Equals, remember a move is, one thing here. Do you know do you remember what data type the move was? Yep, it's a tuple. Tuple of row and column. So you don't need the board's cell, but you need the tuple. And we already have the row and column, right? Which is, yep, you can write it down. Oop. So it's row R, oop, R, yep, and comma C, but you have to wrap that as a tuple. Yep, oop. Yeah, good job. Now we want to finally, after the loop, return the best move. Yep, good job. That's it for the AI move. Good job. And do you have any questions or? Yeah. So for everyone, just to repeat, we set the best score, we set the best move, and these are all random. Although the best score is just set to the lowest possible because we're trying to maximize it. And legal move is we get all the available moves that we can do that are not either AI player or human player. And these cells are all none. And then we go for each row and column of the legal moves. We want to try and set the AI player. We want to get that score of setting that AI player. We want to kind of evaluate what the score will be if the player will win or lose or draw. And then we want to, after that, set it back to none because basically for now, no one actually made a move. We're just trying to evaluate it. we want to then check the scores. Is the current score better than the best score? If so, then we want to set the best score. We want to set the best move. And then in the end, we just want to return that best move. Does that make sense for everyone? If so, Kaden, you can stop sharing your screen. And thank you for going first as well. Okay. Albert, if you want to share your screen, you will implement the Minimax. Okay. Let's actually zoom in. Can you do Control plus? Okay. Do you have the Minimax copy and pasted? I think it's up. Okay. Let's go to the Minimax base. Yeah. It was the one that you were hovering on. Yep. Control A on the whole file. Copy it. Control C. Go back to, yep. Go to up. You'll see that AI, oh, go down, go down. It's like around 216, line 216. You see that arrow button down when you hover on 216? Oh, yep. Click and then delete. Hover on, yep, delete it. Good job. Now we want to go to line 219. Oh, you already have it there, actually, right? You have the Minimax. Do you have the AI move under it? Go down, down, down. Go down, go down, go down. Yeah, you have it. Okay. So let's implement that Minimax. Oh, also, I'll probably actually I already explained the last time. Okay, let's go to Minimax and we'll implement this function. So this is a big function. You have to go up. It's like line 214, something like that. Oh yeah, right there. The Minimax. Yeah, that one. Yep. So basically, you have the board, you get as the arguments, you get the board, you get the def, you get is maximizing, you get AI player and human player. And let's go down to number one, check for terminal state, win, loss, draw. So here we want to check if there's a winner, or if there's a draw, or if you lost. So go to line 252. You'll start implementing the function here. So tab. So let's first check the winner. How would you check the winner? Oh, I think you have a Copilot enabled. Can you do Control Shift P? Copilot, COPI. Let's see. Okay. Disable completions. Do you see that? It's under GitHub Copilot disable completions. It's around the middle. That one. Yep. Now it will be good. Okay, so we set also if you want to enable it back after this, you can do that as well. Uh Winner equals check winner board. Now we want to check if who's the winner. So if you want to do that, Albert, how would you check who the winner is? And remember that we already have the AI player and human player variables passed into the function. One thing you can check, hover on the check winner. Just hover on it. No need to click it. Yep. What does it return? It returns a string and it says X or O. But in this case, it will be AI player or human player because those are the X and O's. So do you have an idea of what you want to do? Because you want to see who the winner is and evaluate the score based on that. You can write it on the inside the code as well. Or let's see this. Do you know of a way to check conditions? How would you check who the winner is? So do you know yeah, if, oh, it's still on for some reason. Anyways, yep, if, and then we do, if the winner is AI player, why is it still on? I wonder. Can you do Control Shift P again and then disable try Copilot? And then, oh, what the hell? Okay, whatever, let's just work with it. So, oh, I think it's that Gemini one. Do you see that on that left, the second to the bottom? Yeah, click on that. Let's see if you can. Weird. Then can you go to the two in blue? It's like five from the bottom. Yeah. And then you see that Gemini Code Assistant? Let's uninstall it for now, and then you can reinstall it later. Yeah. Now let's see. Okay. Anyways, what the AI completed, we check if the winner is AI player, and we return the point 10 minus def. So basically, it's a positive 10, meaning that the winner being AI player is a good thing. And we want to maximize that if you're the AI player. Or if it's the winner is human player, the def minus 10. So this is negative, meaning if you want to minimize it, you want the winner to be human player. Or else you want to check if the board is a draw, in which there's like no point. Now, what's after this? You want to, if the game is not finished, generate all the legal moves. So do you know of a way to generate all the moves? All the legal moves? So click enter. Yeah. How would you generate a list of legal moves? Do you know of a way? Well, the one thing, you already have that function, right? If you go to the top, let's go to the, like one or two more functions above. Yeah, two. You see that get available moves? We can use that, right? And that function, you need to input the board and it gives you a list. So if you want to try and do that, you want to generate all the legal moves. Okay, how about this? Create a variable that you want to set to legal moves. Albert? Yep. Legal, we can do underscore moves, or yeah, that works too. Equals, okay. Yeah, get available board. Okay, let's do up to the second step. So here we get all the legal moves, and if you go up, is that the whole second step? Oh, no, no, still in the same function. Yep. Is that the second step? If the game is not finished, generate all the legal moves. Okay, so it's done. So good job. We'll only implement the first half, and we can get someone else to implement the second half. Thank you, Albert, for sharing your screen. Now going Albert, Kaden, Nicholas, if you can share your screen, we'll just complete the second half. Nicholas? Yep, thank you. Uh, go up. Yep. So number two, we have to recursively explore with beta alpha. Oh, you're in the wrong file. Minimax is the second browser tab. Yep. So number two, go down. We want to branch out to the next level of the game tree. One second. We want to, for each square, simulate the AI and call the minimax function. Or actually, for each move, we want to apply the move. We want to recurse the opposite player. We want to undo the move. So let's start off with going through each available legal move. So although maybe I'll just share you the first half this, or Albert, can you copy and paste the first half to Nicholas in the chat so he can copy and paste? Thank you. And Nicholas, if you can just copy and paste that. Place it in the minimax. Go up. Yeah, right at line 37. Uh, oh, right. You can't copy and paste from Zoom. Okay, just Control Z it. Okay, we'll just implement number two. I'll just have to explain to you. So first, inside that if is maximizing. So go to line 41 and then press enter. Or yeah, 47. So this is maximizing. If it is maximizing is true, then it's the AI's turn. So for this, we want to start with the worst possible score since we're trying to maximize. As it says, line 42, we want to initialize best move to negative infinity, best score. So do you know how to do that? Okay, so let's create a variable named best score. This will be a local variable inside if is maximizing. You don't need to import. It's not a library. Yeah. Go to the top. What you will have to import, go up all the way to line number 1. What you will have to import is the math library. Yep. Do you know why we don't put the import on the best score? You can just say it in the replit or like type it. Oh, I see. Uh, Import is only used for importing from a library or another file, but inside the same file, another function that you can maybe use is called global. So you can do global best score, and that would be kind of global in that file. You can use that variable anywhere. But using import other than the first few lines it won't work since best score is not a library as well. Does that make sense? Okay, so let's set best score. We want to set it to negative infinity. So equals, yeah, negative math dot infinity. Is there a way to disable replit AI? Disable replit AI? I don't think so. Okay. Oh, it says you need to adjust the AI setting within replit. Eh, we don't care about it right now. Let's just
Like
get this finished.
AI thing is like built into Replit. It like the only
Yeah.
way to create a new app is you have to tell AI that you want a new app. It's really annoying.
Oh, I see. Okay, whatever. We don't even need it. Okay, so we want to loop over every empty cell. You know how to do it? Although the AI just tells you, but to help you understand this, basically we get all the available moves from the board, which is the row and column. And this basically is, so it gets all the legal moves, which say there's like 5, then it iterates through each 5 moves. It gets the row and column, and you can use the row and column for anything else. Next, we want to place the AI player in that cell using the row and column that you just got. So how would you do that? Yeah. Yeah, no need to write that whole thing down. Yeah, you could do that, but in this case, you can just set it right away to that board. If you see in the AI generated, you can basically just call the AI player and set that AI player into the board's row and board's column. And do you understand how that indexing works for the board? The board row, board column, board rows column? Yeah. Although you place the AI player into the board's row column. But yeah, you got the idea. Now we want to basically, okay, so we place the AI player in the cell. We want to call the minimax again, but with a higher depth. So we do depth plus one. Also, do you guys understand what depth is? Not even, not only Nicholas has to, if anyone else want to answer that, you can too. Depth, oh no, DEPTH. Sorry, my pronunciation is bad, but depth, yeah. So does anyone know what that is in this case, in Minimax? So if you see in that generated code, does anyone know that what that second argument is? Yeah, so it's basically how far deep you are. So at first, you're right at the top, so you're depth zero, and then each time you go further down, which is when you call minimax, you do add one to that depth. Make sense? Yep, okay. And this is actually important. Does anyone know why depth is important? I'm gonna assume no. So it's basically important because to check the score the move, the value for stuff. Yeah, that's yeah. Actually, that is a full part of it. So let's say there's two main ones. One is to set the value or like the score, and each depth kind of like adds or subtracts from that score depending on if you're maximizing or minimizing. Because each depth you go, you kind of like wasting time. The whole point of like stockfish for chess is because chess, the amount of times because there's so many available moves, the more you think, the more time you waste. And since it's a time-based game, you lose points based on that. So let's finish off this code. Let's just finish off this for loop and then go ahead. So now we want to set the score to minimax. We want to call it score. We want to equals and then do minimax. And inside the minimax function, like that hover of the doctrine tells you, you put in the board, you put in the depth, which is you add one. You set it to false. AI player, human player. And the reason it's false is because the AI player is not trying to maximize. I mean, the human player. Since it's the human player next after the AI move. Make sense? Okay. Next, we want to undo the move. Do you know how to undo the move? Uh, it means like the line on 52. We set the board's row column, that cell, to AI player, right? Now we want to revert that to its original state before we set it to AI player. Make sense? Yeah. Exactly. You got the idea. Yep, to zero. Yep. Although, do you know the value that it was before? The default value? Uh, if you go to tic-tac-toe on the rightmost browser, you don't need to reshare your screen. You can just tap on it. The rightmost browser tab. Now, if you go all the way to the top, initialize board, then you'll see what's that default value. Yep. So let's set it. Actually, since it's just that one cell, do you need a list? Yeah. Good job. And none is capital. Yep. Okay, so we set it to none. Now we want to set the best score. So, yeah. Does everyone know the max function? Anyone need explaining about that? Just takes in two values, gets the max. Yep, you can complete the function. And then we want to return the best score after that for loop. After the for loop. Do you know why it shouldn't be in that inside the for loop? The reason is because you only, so the for loop is for going through each available move, right? So if you do return statement at the end, let's say you go through it once and it hits the return and it only checks one available move. So no matter how many times you do it, you always only check the first move. Does that make sense? Okay. So after we go through each available move, then we want to return the best score. Okay, any questions here? If not, you can stop sharing your screen. And yeah, basically that is it for today in terms of code. Does anyone have any questions? And then we'll go on to Quizlet. But yeah, as you guys can see, these are some hard concepts, and this is the easiest algorithm in AI, like by almost. And it is pretty hard. Once you guys get into like neural links, neural networks, it gets out of hand. Now I will share my screen for Quizlet. Well, during that, I'll also post the YouTube video so you guys can see the, or James, I think it was. If you want to look back at it, you can see it next since you're doing your socials homework. Okay. Also, let me just write a text for next time, next week. I think Nicholas went, Albert went, Aiden want or shared coded in class. Next week we'll move on to not Nicholas, Albert, or Caden to start next, just so that it is fair for everyone. I think it's this. Share. You guys should see my screen. Don't worry, I won't like do too much or like tell you guys to do too much. Only like half a function at most, or like AI move, which is small. So can you guys see my screen? I'm just gonna assume that you can host. Actually, can I change it? Weird. Okay. Send it here. Okay, now you guys can join. I sent the link in the chat. I'll wait for 2 minutes while I stop the Zoom recording.